So this is the structure of a particular N channel JFET, right? Now let us see the operation of this FET, right? So we have a gate terminal, we have a drain terminal, we have a source terminal, right? So current is going to flow within this drain to source terminal, right? So source is the terminal which is going to provide the charges, right? And drain is the terminal where we are going to collect the charges. So as n channel is present, so mostly we will have electrons as the majority charge carriers, right? So source has to generate the electrons, and hence we have to connect this source to negative potential of battery, and here drain terminal to be connected at positive potential, right? Okay, so positive potential will attract electrons from this source towards it, right? And so current will flow from drain to source, but charges will flow from source to drain, right? And whatever the flow of the current will be present there, gate potential that is to be applied at this gate terminal, right? It will affect the flow of those charges and the current. Let us see. Let us first keep gate to source voltage 0, right? Means we will connect this gate and source to this ground is going to have zero potential. At the same time, this source terminal is connected to a negative potential of battery, and drain is connected to positive potential of battery, as we discussed. And we have kept gate to source potential 0, right? And what we will do, we will vary drain to source voltage, that is this VDD. We will vary drain to source voltage, and we will try to observe the effect on this current flowing through this device, right? Through this channel, right? Okay, N channel. Okay. Let us see. So as we are aware, this P and N semiconductor, when connected to each other, this form a PN junction, right? We are already aware that this forms a PN junction. So there is definitely a depletion region present at this junctions, right? Wherever the N and P semiconductor are meeting, there is going to be a depletion region present, right? So we are aware that this depletion region is of course going to vary with respect to what the potential that we are going to apply to this N semiconductor and P semiconductor, right? If the P and N semiconductor are forward bias, then this depletion rate will be smaller. But if the P and N junction are reverse bias, then what is happening? This depletion width will increase, right? That we are aware of, right? Okay. So let us see. So here the terminal is at positive potential, while source terminal is at negative potential. And while we have kept this gate to source potential as 0. So what will happen? The N semiconductor at this drain terminal, the N semiconductor at this drain terminal, which is having what positive potential, while source terminal, it is going to have negative potential. So as we are aware, whenever the positive potential is connected to this semiconductor, right? So what will happen? This P and N junction here at this region, we will have a reverse bias mechanism, right? For this region, right? For this region. So what will happen if we increase the potential, positive potential at drain region? So as we are aware that when this N region is going to have more and more positive potential, so the depletion region will increase. So depletion region will increase. So here this more gray region, which represent the depletion region, it seems to be increasing size at drain terminal, right? So at this drain uh, position, right, at this drain region, right, what we find, this depletion region of this PN junction, right, is increased as compared to what this source, right? Because here we will have more forward potential from source to this gate, but here from this drain to this gate, means from n to p, we have more reverse potential, right? But here from source we have more forward bias potential. So yeah, we can conclude that here at this drain terminal, right, the size of depletion region will increase. How? If we increase the positive potential at this drain terminal. As soon as we increase the drain terminal potential, the depletion region is increasing. But at the same time, we have to remember that electrons are attracted toward this drain, right? From source to this drain. So electrons are attracted toward this drain. So we can say that current is flowing from drain to source, right? At the same time. So as soon as the current is flowing from drain to source, at the same time the depletion region width is going to vary, right? So as soon as we increase the drain potential, this depletion region will increase toward this drain terminal, right? It will get increased toward this drain terminal, right where it comes to in this picture. What we see, it the depletion region is confined toward this p and n junction. But as soon as the drain potential is increased, as soon as drain potential is increased, we will see that this depletion region is moving toward this channel, right? It is more in going into this channel. It is increasing in channel, right? It is more increasing toward this drained terminal, right, from both this p and junction, right? So what will happen to this current? So we see that the drain current, if we increase the drain current, right? If we increase the drain current, right? So as we are increasing the drain voltage, so drain current is also is increasing, right? Okay. So as soon as drain current is increasing with respect to voltage, we can say that there is a linear relationship between applied voltage at drain to source and the drain current ID flow. Means as we increase the drain to source voltage, the drain current from drain to source is also increasing. But we have to remember at the same time that depletion region is also going to increase, right? So we will increase the drain to source voltage such a way that this complete depletion region will touch, or the complete depletion region will overcome over this channel. Means this channel will pinch off. Means we will pinch the channel. How? After increasing the drain to source voltage in so large that the depletion layer, right, towards this drain terminal, right, is increased, right? The width of depletion region is increased so that from the both PN junction, what we find, the depletion region is increased in a such a manner within this device that complete channel is overcome by this depletion region, right? We can see here the region, depletion region is, yeah, connected here completely, or it has, yeah, it has pinched this complete n channel, right? Here the whatever the n channel was there, right, it has now pinched by this depletion region, right? Depletion region is connected here, so we can say that the complete depletion region has occupied this n channel at this terminal. So as the depletion region is completely present here, right? So we can say that when depletion region is more, right? So what happens to the current? So there will be no flow of current, but it will be not the case, right? So what will be happening, right? There will be a limitation of the flow of current, right? There will be a limitation to the flow of current, right? Okay. So whenever this channel is pinch off, right, at the voltage where we applied the drain to source voltage, at that particular voltage, when this channel pinch off or this channel touches, or the maximum yeah, maximum depletion region is present over this channel. Okay, so channel is pinch off, that particular voltage is called pinch off voltage, and we denote it by vp. We denote it by vp. Okay, pinch off voltage. So what will happen if we again increase the drain to source voltage after this pinch of voltage. So what we will get? We will get a constant current. We will get a limited current. Okay. So if we try to plot the characteristics, we will get like this. Okay. So we call these characteristics as drain characteristics, right? Okay. So why? We are going to plot the relationship between the drain to source voltage and drain current. Okay, drain current. So as soon as this drain to source is increase, what we will find? What we will find as soon as drain to source is current is increased, what we will find current is linearly increasing. So current is linearly increasing. So this region blue line, this current is linearly increasing. But when it comes to the pinch off point, when it comes to the pinch off point, right, when VDS equals to pinch off voltage, this channel will pinch off. So here, right, when the voltage VDS equals to pinch off voltage, yeah, we will get a constant current. We will get a constant current flowing through this drain to source, right? Constant current. So there is going to be limit of flow of current. A constant current will flow, right? Because channel is pinched off. So because of the depletion area, it will try to, yeah, it will try to resist the flow of the current, right? Two, three from drain to source. So only constant current will be flowing through this drain to source. So this straight line represents the constant current. So whatever we are operation is yeah, whatever operation is happening right now, it is happening when we have kept gate to source equals to 0, right? Gate to source voltage equals to 0. Gate to source voltage is 0, and we are increasing drain to source. So we will get such characteristics, right? So first, as soon as drain to source voltage is increased, there will be linear relationship between the current, right? Current and the voltage from drain to source, right? So current is increasing linearly, but up to what? Pinch off point. Up to what? Pinch off. At pinch off point, this depletion region will pinch off. There will be maximum depletion layer, right? Oh, sorry, n region will be pinch off, and there will be maximum depletion layer, right? And so after that, yeah, we will get a constant current. Okay. After, if we increase the VDS after this pinch off point, we will get the constant flow of current. Okay. And we call that the device is in saturation region. Device is in saturation because we are getting the maximum constant current, right? And we call this current as IDSS. Okay. Saturated short current. Okay. Or short drain current. Drain short current. Okay. Drain to source short current or saturated current, IDSS, at which VGS equals to 0. When VGS equals to 0, and after pinch of point, whatever the current we are getting, we call it a short drain to source current or saturation current. Okay. Yeah. So this is how the characteristics for drain, this FET is there. We call this a drain to source, or we call it as a drain characteristics, right? We have to plot between drain to source, and the drain current that is flowing from drain to source, keeping gate to source, right? Okay. So what we have a particular region where linear region is called, yeah, resistor. It is a linear resistance region, right? Because the current is varying linearly with this drain to source voltage. Okay. And after that, we have the saturation region. What we get a constant IDSS value, right? Constant ID current. Okay. So if we try to put the VI characteristics, it will be look like this. We have a ohmic region, and then after it, a pinch of region. Okay. So if we again increase the more and more voltage drain to source voltage, so what will happen is that there will be a breakdown of the device. There will be a avalanche breakdown of the device, right? We are already aware of avalanche breakdown, where the bonds will be break of this channel. Whatever the semiconductor atoms are present in the channel, those their bond will be broken, and we will get this avalanche breakdown. And after which, this device will be of no use. Okay, so that particular point, The particular voltage is called avalanche voltage, right? So we will get the characteristics like this is a drain characteristic, so we are characteristics like this. Okay, we will have ohmic region where the current will be increasing linearly with respect to the drain to source voltage applied. Then we will have a pinch off voltage, after which the channel will pinch off and we will get a constant current. So we will say that this is the pinch off region, and we will get say that we will get a saturated current, right? And after that we will have the breakdown region. Okay, so this is happening in case of what we have kept gate to source voltage equals to 0. Okay, so this is the characteristics when we could get to source is equal to 0, right? Okay. Okay, yeah, this is the characteristic when we kept gate to source equals to 0. Okay, now what we are going to do, we will vary gate to source voltage, right? Now we will vary the gate to source voltage, right? So this gate to source voltage, we will apply the negative potential at this gate to source voltage. So what will happen when we apply this negative gate to source voltage, right? Okay, or we will increase the gate to source voltage. So what is going to happen, let us see. So as P and N junction, as P and N junction will get reverse bias because D is already at positive, right? So N is connected with positive potential, and gate which is supplied with negative potential, which is nothing but P type semiconductor, right? So P will get a negative potential. So P is having negative potential, N is having positive potential. So we can say that this depletion region or PN junction is what at reverse bias. So if we increase the gate to source negative potential, so this depletion region will again increase more and more fast. Okay, so while we have kept gate to source get voltage 0, previously having we were previously having drain to source voltage positive, and we varied the drain to source voltage. So we had that the depletion region was increasing with drain to source increased voltage, right? Okay, if and again if we increase the gate to source voltage, negative potential gate to source, okay, if we increase it, so it will again rapidly increase the depletion width. So it will again rapidly increase the depletion width. So the depletion region will again increase more fastly when we apply gate to source. Whatever the depletion region or pinch of voltage or pinch of region was happening when we applied drain to source voltage and keeping gate to source voltage 0, that process will become fast. That process will become fast when we apply gate to source voltage negative potential. So pinch off process, the pinch off of the channel process will become fast. It will get fast. So whenever we are having these gate characteristics drain to source characteristics, right? Yeah, when we keep this gate to source potential equals to 0, so this will turn fast, right? Means what, this line will shift to down. Okay, means what, it will appear more fast, right? It will appear more fast. So this line will get shift down, right, as soon as we increase the gate to source potential. So this is how the characteristics will look like. So from 0, if we increase the potential to the -1, so this curve will shift to down, right? So we will get this current, that is saturation current, more earlier as possible. So if we again increase this -1 to -2, we will we will have shifted this characteristics more down, right? So we will have saturation region more fast. Okay, right? So as soon as we increase this gate to source voltage more and more negative, and when it comes to the value of pinch of voltage, when it comes to the value of pinch of voltage, what we will get, very less or minute current will be flowing at, okay, very less, okay, in the order of micro ampere. So we can say that nearly negligible current is flowing through this device, right? Or no current is flowing through this device, where when the gate to source voltage applied is equals to what, pinch of voltage. Okay, So we will get no current, nearly no current flowing through this device. So we can say that there is no current that much is able to operate the device or whatever the circuit. So we will say that the device is turn off. So this is the region where the device is going to turn, or we say that the region is operating on cut off region. The region is going to operate in cut off region, right? So below which VGS equals to VP, pinch of voltage. So we will get this kind of characteristics. So we will as well get to source negative potential increase, curve will get shifted, right? Okay. So we will have three regions: a cutoff region below what VGS equals to pinch of voltage VP. We will have a ohmic region like this curves, right? And we will have a saturation region after this ohmic region and above this, yeah, cutoff region, right? So this is how the drain characteristics will look like when all the voltages of gate to source voltage and the drain to source voltage are applied. Okay. Yeah. Okay. So this is how a particular characteristics we will have, right? Ohmic region, then a saturation region, then a cutoff region, right? So for ohmic region, right, indicated in red box, there is a relation between the current and the voltage VDS, right? That is a linear region, linear relationship. So of course, this device is going to provide a input resistance, right? This resistance, there will be a certain resistance present in input resistance. That resistance is nothing but what dynamic resistance. Because why it is dynamic resistance? Because all the values of the VDS and the ID are varying, right? All the values of VDS and IDS are varying. So whenever the values are varying, we call as the dynamic. Okay, when the values are fixed, we call it as static characteristics. So we have these dynamic characteristics present, so we will have a varying type of resistance. Okay, so we call this resistance as dynamic resistance. Okay, we call this resistance as dynamic resistance. Okay, so how we calculate this dynamic resistance? With we have the formula R0 upon 1 minus VGS upon VP square. Okay, when yeah, when VGS is equals to 0, so this line indicates, right? When VGS equals to 0, so this device is going to offer the particular resistance, right? So R0 is that value of resistance, then VGS is kept 0. Okay, then we will calculate dynamic resistance with the help of this formula. Okay, so yeah, so we have this kind of characteristics. Or and when it comes to this P channel FET, right? P channel FET, what is going to be the difference? Instead of gate to source negative voltage, which was in case of N channel, we were having negative gate to source voltage. In case of P channel, we will apply positive voltage. So we will have the similar curve, but only the difference is that as soon as the positive potential is increased, so we will have the reduced current, right? Like this, the similar characteristics, right? As that was having in case of N channel, it is similar to P channel. Okay, it is similar to P channel and N channel is going to have similar characteristic, but the value of VGS is different. In case of N channel, value of VGS is negative, and in case of P channel, value of VGS is positive. And after we increase the VDS more and more, so we will have the breakdown region, right? So as we have seen earlier here, like this ohmic region, pinch off region, and breakdown region. So all P type and N channel, P and N channel both is going to have similar characteristics, right? Right, there will be a like ohmic region, saturation region here up to this ohmic region, then here saturation region, and this breakdown region. Okay, so this is how we have the drain characteristics of the particular, yeah, FET. And this is the symbols, right, for N channel and P channel, right? So gate to source here, voltage we have to apply. We have to apply drain to source voltage. Drain to current will flow from drain to source, right? And gate is going to control the drain and source current, drain to source current. So this is the arrow for this N channel FET inward, right? Arrow is inward toward this drain and source channel. And when in case of P channel, the arrow is outward. Okay.